Welcome to Talk Tensors.
It's great to be here.
Today, we are looking at a paper that I think, well, it fundamentally changes how we should be looking at the intersection of large language models and the actual messy, practical world of software development.
It really does. We're talking about agents. We're talking about tool use.
And we are talking about a really important paper titled Gorilla, Large Language Model Connected with Massive APIs.
Yeah, this one comes out of UC Berkeley and Microsoft Research, and it's a landmark piece of work. What I love about it is that it really stops treating the LLM as just, a chatbot or a creative writing assistant.
Right.
It starts treating it as an interface, maybe even the primary interface to all of our computing infrastructure.
That's always been the dream, hasn't it? We've got these incredible reasoning engines and we want them to, book our flights or run data analysis or spin up servers for us. We want them to use tools.
But the reality is they're clumsy.
Clumsy is a very polite way of putting it. They're often just wrong. And the paper identifies a very specific and I think very painful problem.
They call it hallucination in the tool shed.
Hallucination in the tool shed. I love that phrase. It sounds like a horror movie for developers, which, sometimes it is.
It absolutely is, because this is the core failure mode. You ask a state-of-the-art model, we're talking even GPT-4, even Claude, to do a specific technical task with a specific library.
Sure.
And it will often just invent an API call, a call that looks perfectly plausible, follows all the linguistic rules of code, but it simply does not exist.
It's literally gaslighting you with Python code.
That's a perfect way to describe it. And the paper opens with this fantastic, crystal clear example of this happening. The Snakers 4 example.
Oh, it's classic. I think anyone who's tried to use these models for serious coding has run into a version of this.
We should probably walk through it.
Yeah, let's do it. So the authors prompted GPT-4 with a very reasonable request, something like, help me find an ATI to convert the spoken language in a recorded audio to text using Tensor Hub.
A totally standard request a developer might make, something you'd see in a Jira ticket.
Exactly. And GPT-4, being the confident assistant it is, says, sure, here's the code for that.
And it generates a Python script, looks good on the surface, it imports Torch, calls the right function, torch.hub.load.
But then it tries to load a model called Snakers 4 Celero models.
Which sounds so real.
It sounds incredibly real. Snakers 4 sounds like a legit GitHub username. Celero models sounds like a real model repository. It has all the right patterns.
But if you actually copy-paste that code and run
it crashes an error because that specific model address in that context, it's just not there. It was completely made up. The model hallucinated a tool.
That is the real danger, isn't it? It's not just wrong, it's plausibly wrong. It looks right to the human eye, so you waste time debugging it, thinking you did something wrong.
Right. And they didn't just test GPT-4, they ran the same prompt through Claude as well, didn't they?
They did, and Claude failed in a different but equally wrong way.
It picked the wrong library entirely. It tried to use torsadio.pipelines, which, again, syntactically, that looks correct. It's a real thing.
But it wasn't the right tool for the specific constraint of the prompt, which was using Tensor Hub. It ignored a key instruction.
So you have one model inventing tools and another one ignoring your requirements. This really sets the stage for the paper's main character, which is Gorilla.
And the thesis here, the core argument, seems to be that while LLMs are amazing at reasoning in the abstract, they're fundamentally limited by their static nature when they try to touch the real world.
That is the absolute crux of it. I mean, think about what a large language model actually is. It's a fixed set of weights, a static computation graph.
It's a snapshot.
Exactly, a snapshot from when it was trained. But the software world, the world of APIs, cloud services, libraries like PyTorch, TensorFlow, Hugging Face, that world changes every single day.
Every hour sometimes. New versions, deprecated functions, different arguments.
Constant change. So if you're relying on a model's internal memory, its weights, to know how to call an API, you're relying on a photograph of the past. It's guaranteed to become outdated.
Which is why the authors argue that the solution isn't just about building bigger and bigger models with more and more parameters.
No, it's about building them smarter. The solution they propose is a very specific type of fine-tuning that makes the model retriever aware.
And that's what Gorilla is. It's a fine-tuned, llama-based model, and it's designed from the ground up to surpass GPT-4 specifically at this one task, writing accurate API calls.
And what's wild is that it's based on Llama has 7B. In the grand scheme of things today, that's a relatively small model.
A David versus Goliath situation.
It really is. But because of how they trained it, which we're definitely going to get into, it just punches way, way above its weight class.
Before we dive into the how, I want to stick with the why for just another minute. The paper makes this important point about the transition from a small set of hand-coded tools
right to what they call a vast space of changing cloud APIs.
Yeah, that's a key distinction. A lot of the earlier work in this space, things like Toolformer or the first AI plugins, they usually dealt with a handful of tools.
Like a calculator, a calendar, a translation API.
Exactly. Stuff you could easily describe and hard code into the system prompt. You could write out the function definitions for 10 tools and just stick it in the context window.
But the paper talks about massive APIs. They're not talking about 10 tools.
No. We're talking about hundreds of thousands, potentially millions of tools. You can't fit the documentation for every API on the internet into the context window of an LLM. It's computationally impossible.
So you can't just give the model a bigger instruction manual.
You can't. So you need a system that can do two things. First, it has to dynamically retrieve the right documentation for the task at hand. And second, and this is the absolute key, it has to correctly interpret that documentation to write the code.
So Gorilla isn't just a model that was forced to memorize more APIs.
It's a model that was taught how to read the manual.
That's it. It's the teach a man to fish philosophy, but for AI agents. Instead of giving the model the final answer, they trained it to use the fishing rod, which is the documentation.
Okay, that makes sense. So let's unpack the methodology. How do they actually build this thing? I think the first step was recognizing that they couldn't even test their idea without a new benchmark.
Exactly. Your standard NLP benchmarks, question answering, summarization, they don't cover this massive API problem, so they had to build their own. They built API Bench.
And API Bench is a beast. It feels like a massive engineering project in its own right.
It is. They knew that if you want to test an agent's ability to use real-world tools, you have to get data from the real world. So they went to the 3 biggest hubs where developers and researchers actually share machine learning models.
Torch Hub, Tensor Hub, and Hugging Face.
The big 3. And these are not small, tidy repositories.
No, not at all. For Torch Hub, they were pretty exhaustive. They grabbed everything, which was about 94 distinct API calls. For Tensor Hub, they got the latest version V2, which came out to around 696 API calls.
And then there's Hugging Face.
The Wild West.
It's a jungle. I mean, there are hundreds of thousands of models on there. It's huge. It's noisy. The documentation quality is all over the place.
So scraping everything was out of the question.
Completely impractical. So they made a smart choice. They filtered for the top 20 most popular models within each task category, computer vision, NLP, audio, multimodal, and so on. That gave them a manageable, high-quality slice of about 925 models.
So in total, the final data set has 1,645 API calls?
Something like that, yeah. So they have this huge collection of models, but an agent doesn't just need the model file. It needs to know how to call it. It needs the instructions.
Right, it needs the documentation.
So this was the next crucial step. They took the model cards, which are basically the documentation pages for these models written by humans, and they converted them into a structured JSON format.
They standardized the mess. This feels incredibly important.
It's the core of the whole data pipeline. They created these clean, machine-readable objects that contain specific fields, like domain is vision or text-framework.pytorch or TensorFlow.def functionality, the actual apical, the AB arguments.
And environment requirements. That one seems super important for actually running the code. Knowing you need Python 3.7 or a specific version of CUDA or PyTorch.
It's critical for execution because if the agent generates code that is syntactically perfect, but the environment isn't set up right, the agent has failed. The code will crash. So that context is vital.
Okay, so they have all this structured data about the tools, the answers, so to speak. But a data set needs questions, right? You need to train the model on a user asks X, agent does Y format. How do they generate the user side of that equation?
This is where they use the self-instruct method and they use GPT-4 to do it, but and this is really clever, they designed the process to prevent the model from cheating.
Cheating how? What would that even look like?
Well, think about it. If you just give GPT-4 the API documentation for, say, ResNet 50 and say, generate a user question for this API, what is it going to do?
It'll probably say, how do I use ResNet 50 for image classification?
Exactly. It'll use the ATI's name in the prompt. And if that's your training data, the model you're training doesn't learn to reason, it just learns to pattern match. It sees ResNet 50 in the question and ResNet 50 in the docs and connects the dots.
So it becomes just a simple keyword search rather than a semantic understanding of the user's intent.
Precisely. So to get around this, they used what they call a blind prompting strategy. They gave GPT-4 the API documentation, but they specifically instructed it not to use the API names or any unique identifiers in the user instructions it generated.
So instead of use ResNet 50 to classify this image, the prompt GPT-4 generates would be something more like, I need a highly accurate model to identify the main object in a photograph.
Exactly that. This forces the gorilla model during training to actually understand the functionality described in the JSON documentation. This is a convolutional neural network for image classification, and match it to the user's abstract intent rather than just matching string tokens. It's a much harder and much more useful task.
And that process resulted in over 16,000 of these high-quality instruction API pairs. And that's the fuel they use to train Gorilla.
That's the fuel. And this brings us to the actual architecture and how it works, because Gorilla can operate in two distinct modes. Understanding the difference between them is really the key to the whole paper.
Right. There's the zero-shot mode and then the retrieval mode.
So in zero-shot mode, it's pretty straightforward. You ask Gorilla a question, and it produces the API call straight from its internal weights. It's relying on what it learned and memorized during that fine-tuning process.
Which is already going to be impressive, just because it was trained on that massive, super clean, well-structured data set.
It is. It's already a very capable model in that mode. But the real magic, the part that solves the static knowledge problem, is the retrieval mode.
Okay, break that down.
In this mode, the system first takes the user's prompt. Then it uses that prompt to search a database, a vector database containing all those JSON objects from API Bench to find the most relevant API documentation.
And then it just appends that documentation to the prompt.
Exactly. The final prompt that goes to the Gorilla LLM is a combination of the user's original question plus the retrieved JSON documentation.
So the full prompt would look something like, user, find me a good model for text-to-speech, context. Here is the full JSON documentation for the Celero TPS models.
Precisely. And the training process for Gorilla was designed specifically to exploit the structure. They call it retriever-aware fine-tuning.
What does that mean in practice? How is it different from just, in-context learning?
The difference is in the training data format. The instruction prompt they used during the fine-tuning explicitly included a special section that said, use this API documentation for reference, retrieved app.json.
So that phrase, use this API documentation for reference, was part of the training data itself. Why is that so important? Why not just shove the data into the context window and let the model figure it out?
Because standard language models, even the big ones, can get confused by a lot of extra context. They might ignore it, or they might suffer from, the lost in the middle problem where they only pay attention to the beginning and end of the prompt.
Or they might just default to their own pre-trained knowledge.
Right.
They might trust what they already know more than this new piece of text you just gave them.
Exactly. By fine-tuning with this specific explicit structure, they effectively taught Gorilla a new skill: to prioritize the retrieved documentation over its own internal memory. They taught it to trust the manual more than its intuition.
That makes so much sense. So they're literally teaching it to parse the second half of the prompt, the documentation, in order to generate the correct answer for the first half, the user's question.
Precisely. And this is the mechanism that enables the adaptability we were talking about earlier. If that API documentation changes at test time, let's say the library updates, and an argument changes from pre-trained true to weights default.
Which happens all the time.
All the time. A normal model would fail. It would generate the old code it memorized. But Gorilla, because it's been trained to read the manual, will see the new weights default argument in the retrieved JSON, and it will write the correct updated code.
So that solves the brittleness problem. It completely decouples the model's knowledge from the ever-changing state of the real world.
It does. You don't need to retrain the entire multi-billion parameter model every time a developer on GitHub changes a function name. You just update a single entry in your retrieval database. It's infinitely more efficient.
Okay, I think I have a good handle on the training, but I want to talk about how they graded this. Because grading code is notoriously hard.
It's a huge challenge.
Right. If I write a function and I put a space in a different place than you, or I use a default argument that you spelled out explicitly. A standard text comparison is going to say, my code is wrong, even though it runs perfectly.
Yeah, traditional text-based metrics like BLEU scores or just exact string matching are completely useless for code. As you said, there are dozens of valid ways to write the same API call. Maybe I explicitly state pre-trained true, or maybe I leave it out because true is the default value.
Both are correct. But string matching would fail one of them.
It would mark it as a 0, so they needed something much more intelligent.
What do they use?
They used AST subtree matching.
AST, that stands for abstract syntax tree.
Right. It sounds complicated, but the concept is pretty simple. When a computer, like a compiler or an interpreter, reads code, it doesn't just see a string of characters. It parses it and breaks it down into a logical tree structure.
So the root of the tree might be the function call itself. The branches are the arguments, and the leaves are the values you're passing to those arguments.
Exactly. So instead of comparing the text torch.hub.load, they're comparing the structure of the code's tree. They parse the code that Gorilla generates into an AST. Then they find the specific subtree that's rooted at the API call they care about.
And then they just check the branches of that subtree.
Yep. They check, is the function name correct? Is the repo argument pointing to the right place? Is the model argument correct? And so on. It's comparing the semantics of the code, not the syntax.
And this robust evaluation method allowed them to make a really helpful distinction between a hallucination and an error. I found that part of the paper really clarifying.
It's a critical distinction if you're trying to build reliable agents. A hallucination, according to their definition, is when the model invokes a tool that simply isn't in their database. It's an imagined tool.
So the Snickers 4 example from GPT-4 is a classic hallucination.
Perfect example. An error, on the other hand, is when the model invokes the right tool, but it does it incorrectly.
So it calls the right function, but maybe it misses a required argument or passes a string where an integer was expected.
Exactly. So hallucination is I'm making things up, and an error is I'm just being clumsy.
And you really want to eliminate the hallucinations. Errors can often be caught and fixed, right? You can read the error message from the interpreter, look up the docs again, and try again.
But a hallucination sends you down this wild goose chase, debugging something that doesn't even exist. It's a complete waste of time.
So with all that set up, the data set, the training, the evaluation, let's get to the scoreboard. How did Gorilla actually do?
It crushed it. I mean, there's no other way to put it. In terms of API functionality accuracy, Gorilla, again, a 7 billion parameter model, outperformed GPT-4.
That is it's massive. A 7B open source model beating the flagship closed source giant on a complex coding task.
It really just highlights the incredible power of high-quality, domain-specific fine-tuning. A smaller, specialized model can absolutely outperform a larger, generalist one on a specific task.
And this was true even in the zero-shot setting, right? Without the retriever helping it.
Yes. Even when it was just relying on its internal weights, Gorilla achieved state-of-the-art results. That shows that the fine-tuning process itself managed to bake a huge amount of practical knowledge into the model's parameters.
But then when you add the retriever at inference time, it gets even better.
It does. And this is where we get to that really surprising finding from the paper. When they looked specifically at the hallucination rates, they found something very weird with the big general-purpose baseline models.
This is the GPT 3.5 versus GPT-4 thing.
Exactly. In some of the tests, specifically on the Torch Hub and Hugging Face datasets, GPT 3.5 actually hallucinated less than GPT-4.
Which is completely counterintuitive. GPT-4 is supposed to be the smarter, more capable, more truthful model. It should be less prone to making things up.
You would think so, right? The authors speculate, and I think this is a very plausible explanation, that it might be an unintended side effect of RLHF.
Reinforcement learning from human feedback. The process that makes models better chat partners.
Right. RLHF is designed to make models helpful, harmless, and conversational. It trains them to give satisfying answers to humans. And it's possible that GPT-4 has been tuned so aggressively to be helpful that it prioritizes giving an answer over giving no answer.
So if it doesn't know the correct API, its training pushes it to invent one that looks correct, rather than just saying, I don't know.
It wants to please the user so badly that it ends up lying to them. It's optimized for plausibility, not for factual correctness in this very niche technical domain. It mimics the pattern of a helpful response. Oh, you want a speech-to-text library? Here is something that looks exactly like a speech-to-text library.
Whereas Gorilla, which was fine-tuned on this very rigorous instruction API dataset without that conversational layer, is just optimized for correctness. Full stop.
Exactly. And this was reinforced when they tried adding retrieval to the other models. When they gave the documentation to stock Llama or to GPT 3.5, it often didn't help much. Sometimes it even hurt performance.
How could giving it the answer key possibly hurt performance?
Because those base models weren't trained on how to use the answer key, it's like giving a student who has never seen a calculator the most advanced TI-89 and expecting them to ace a calculus exam. The tool is powerful, but they don't know how to use it.
So they get distracted by the extra context.
They do. They see the JSON, but they might not know how to map the fields in the JSON to the specific arguments in the code. But Gorilla was specifically trained for that task. When you see this JSON, you will use these fields to construct this API call. It knows how to maximize the utility of the retrieved information.
This brings us to the adaptability tests, which I think is where the whole concept really proves its worth. Because the world isn't static. The paper describes a scenario where an API changes its name or its arguments after the model has already been trained.
This is the ultimate test of an agent, right? Can it handle change? They simulated a situation where the documentation in the retrieval database is updated. For example, a model's backbone is updated from ResNet 50 to ResNet 101.
And Gorilla handled it
Flawlessly. Because of that retriever-aware training, it didn't just default to what it saw thousands of times during training. It read the new JSON, saw the string ResNet 101, and correctly wrote the code to load ResNet 101.
It ignored the memorized pattern because the immediate context told it to.
Exactly. This implies that Gorilla isn't just reciting code snippets it has seen before, it's actually reasoning about the relationship between the documentation and the task. It's functioning as a dynamic translation layer.
It translates user intent plus technical specification into executable code.
A perfect summary.
Wow.
And there was one other capability they tested that I think is just crucial for real-world engineering projects: constraint satisfaction.
Yes. This is so big, because in the real world, you don't just ask for an image classifier.
Never. You ask for an image classifier that's small enough to run on a mobile device, or one that has an accuracy greater than 70% on this specific benchmark.
Or I need a model that has fewer than 10 million parameters because of my memory budget.
Right. And most general purpose LLMs really struggle with this. They'll just ignore the constraint and pick the most popular, most famous model, which is usually huge, like a big vision transformer.
But Gorilla didn't.
No. It showed a really strong ability to reason about these numerical and categorical constraints. It would look at the metadata in the retrieved JSON, where the parameter count or the license is listed, and it would select the specific DenseNet configuration that actually fit the user's criteria.
So it's not just coding. It's actually performing the engineering task of trade-off analysis.
At a micro level, yes. It's making architectural decisions, not just writing boilerplate.
So if we zoom out and put it all together, we have a comprehensive and novel data set, API bench.
We have a new training method, retriever-aware fine-tuning.
And we have a rigorous and appropriate evaluation metric, AST matching.
And the result of all that is a small, specialized model that can beat the giants by being smarter, not just bigger.
And the authors didn't just keep this to themselves. They released the code, the model, and all 11,000 plus instruction API pairs to the community.
Yeah, they really emphasized that aspect. And they mentioned an important reason for it: mitigating potential biases in which tools AI agents recommend.
That's a really interesting point.
It is. If your training data only contains APIs from big tech companies, then your agent will only ever recommend tools from big tech companies. It might ignore better, more efficient open source alternatives.
So by opening up the data set, they allow the community to audit it and expand it, ensuring the tool selection process is more transparent and fair.
It's vital for a healthy ecosystem. This paper really feels like it laid the groundwork for the agentic future that we're all trying to build right now.
I agree. The core idea that an LLM should act as a dynamic router that connects user intent to other pieces of software, that's the heart of modern agent architecture. Gorilla was one of the first to prove you could build that router reliably without needing a trillion parameters if you just train it on the right data structure.
It's the shift from chatbot to system controller.
From generating text to generating actions.
Well, speaking of generating actions and maybe getting a little creative and outlandish with where this all could go, I think it's time for our favorite segment.
Oh, I am ready. It is time for Novel Notions.
Let's hear it. What have you got for us?
All right. Disclaimer. The following ideas are for entertainment purposes only. Do not build these and then blame us when they achieve sentience and take over your GitHub repository.
Please don't. We have enough problems.
Okay. Notion number 1. I'm calling this the self-deprecating API cleaner.
Self-deprecating. Is the AI apologizing for its own code?
No, not quite. Think about that AST matching capability and the constraint reasoning we just talked about. Now, imagine an agentic system built on the Gorilla architecture. But its main job isn't to use APIs to serve a user.
Okay. So what's its job?
Its job is to proactively test the entire internet's software infrastructure.
So like a chaos monkey, but constructive.
Exactly. It constantly crawls TorchHub, Hugging Face, PyPI, GitHub. It's continuously generating little sanity check prompts for every public API it can find. It tries to write code to use them over and over again.
So it's just running millions of unit tests on the public web 24/7.
Yes. And here's the kicker. When it encounters a broken or a hallucination-inducing API, a library that's documented so poorly that even this super smart AI can't figure it out, or where the documentation says one thing but the code actually requires another, it doesn't just file an error report.
What does it do?
It autonomously generates a patch, or maybe just a wrapper. It creates a new correct JSON documentation file that accurately reflects the reality of how the code works. It then submits a pull request, or maybe just stores this corrected documentation in its own database.
Wow. So it's effectively refactoring the web's backend to be more AI readable.
You're creating a self-healing layer over the internet's code. It's this beautiful symbiotic loop. The AI fixes the tools that it uses, which makes it more efficient at using them the next time around, for itself and for other AIs.
It's like an army of digital janitors paving the dirt roads of the internet so the autonomous cars can drive faster. I love that. Okay, I'm sold. What's notion number 2?
Notion number 2, the just-in-time toolsmith.
Toolsmith. Okay, go on.
So we established that Gorilla retrieves existing tools from a database, but we also saw that it understands constraints and environment requirements at a deep level. What if we extend that retriever-aware training to a generative level?
You mean creating tools that don't exist yet?
Exactly. Imagine the agent gets a request with a very specific niche constraint. Something like, I need an image classification model that uses less than 1 kilobyte of memory at runtime.
Nothing in the database is going to fit that. It's an impossible constraint for existing models.
Right. Instead of giving up and saying, no tool found, it uses its deep knowledge of code patterns and environment requirement from APIBench to write a brand new micro tool on the fly. A tiny, highly specialized Python script that solves that one specific problem.
And then what?
And then it documents its own creation in that standard JSON format, adds that JSON object to its own temporary retrieval index, and then immediately calls the tool it just invented.
Whoa. Okay, so the entire paradigm of a fixed set of tools just... It vanishes.
Completely. The agent literally builds its own ladder as it climbs. It populates a personal, ephemeral Gorilla hub with potentially billions of disposable single-use tools that exist only for a moment.
That completely changes the economics of software development. You don't build general-purpose libraries anymore. You just state your hyper-specific problem, and the perfect library for it exists for the 5 milliseconds it takes to solve it, and then it just dissolves back into nothing.
Disposable software, the ultimate serverless function, created by an AI, for an AI.
That is both incredibly efficient and a potential nightmare to debug.
Hey, that's a problem for the self-deprecating API cleaner to solve later.
Touché. That's a good point. So I guess to bring this all back down to earth, what does this all mean for you, the listener?
I think it means that if you're building agents, or even just using them in your daily work, you have to start thinking very carefully about how you're feeding them information. Are you giving them the manual? Or are you just hoping they remember what was on the test a year ago?
And it means that the future of truly capable AI isn't just about building bigger, smarter models. It's about building models that are better connected, more grounded, and more adaptable to the real, messy world around them.
As always, the link to the paper, Gorilla, large language model connected with massive APIs, is in the description. It is absolutely worth your time to read it.
It really is a foundational text.
Thanks for listening to Doc Tensors. Keep learning.
We'll see you next time.